Hey guys, just gonna record some solutions for assignment 3 for math 30 to 72. Okay, question 1. You have to compute the commutator subgroups of D4, D5, and the Quaternions. Okay, let's do that. How should we do it? So we compute. Okay. Let's start with D4. Okay, let's write down our definition of D4. Is a group generated by A and B, satisfying the relations a to the fourth is E, B squared is E, BA is A cubed B. This is kind of like, this is almost commutative, you know, except for this pesky 3. Okay. So first of all, we know that the commutator subgroup is generated by the commutators of all the elements of D4. Okay, so one thing you could do is just to calculate the commutator of A to the I, B to the J, with A to the K, B to the L. Compute all those different commutators. Put them all, and you know they generate some subgroup of D4, and that's a commutator subgroup. Okay, actually this is not so bad because I mean it's a little complicated, but it would probably be fine. Okay, that's one way to go. Another way to go is, so I'll just put dots, but another way is just to start, like, just compute some different commutators. So let's start with the commutator of A and B. Let's just A, B, A inverse, B inverse. But A to the fourth is the identity, so A inverse is really A cubed. And in fact, you can see that B A inverse is just AB. Why is that? Well, take this equation. So multiply on the right by A and on the left by A cubed. You get A cubed B. A inverse A equals A to the fourth B A, and A to the fourth is the identity. A inverse A is the identity, so you get A cubed B is just BA. In other words, you get this same relation back. So if you start from this relation, you get this relation. So BA inverse equals AB, or you could just use PA cubed equals AB. We proved that in class at some point. Okay. So anyways, A inverse, B inverse, that's just A, B inverse is just A squared. Okay. Now let's let K be the subgroup generated by A squared. One thing we know is that the K is a subgroup of the commutator subgroup, because K is generated by one particular commutator. D4 prime is generated by all the commutators. Okay. Now, from class theorem, if we can show that D4 mod K is abelian, that would imply that the commutator subgroup is contained in K. Okay, so let's do that. Let's try and show that D4 mod K is abelian. Okay, so in D4 mod K, the elements, so D4 mod K, like since D4 is generated by A and B, D4 mod K is generated by the cosets of A and B. Okay, let A bar and B bar just denote the left cosets of K, AK, BK. And now if you compute the commutator of A bar and B bar, but that's just the bar of the commutator of A and B, which is, and the commutator of A and B is A squared bar. Okay. But A squared is in K, so the commutator of A bar and B bar is just the identity of D4 mod K. We'll call that E bar, right? So let me just write it aside here. What is the bar? If G is in D4, then G bar is really just the coset of K corresponding to G. Okay, so the commutator of A bar and B bar is the identity, so A bar commutes with B bar. So also D4 mod K is generated by A bar and B bar, and A bar and B bar commute, so D4 mod K is abelian, since A bar B bar is B bar A bar. I'm very sorry for not moving this up. Okay. So D4 mod K is abelian. That proves that D4 prime is contained in K, and of course K is contained in D4 prime, so they're equal. So D4 prime is just generated by A squared. Okay. Let's compute D5 prime. The strategy is the same. We'll compute the commutator of A and B, but the result, it turns out to be different. Okay, so let's start by computing the commutator of A and B. D5, compute AB, which is just AB, A inverse, B inverse, and still B A inverse is just A AB. So we get the same thing. We get A squared as the commutator of A and B. Okay, but now the difference is that the subgroup generated by A squared is a lot bigger than in D5 than it is in D4. So we let K be the subgroup generated by A squared. We take powers of A squared. What do we get? Well, the 0th power, that's the identity. We get A squared, we get A to the 4th, we get A to the 6th. Since we're in D5, let me just remind you, D5 is generated by A and B. A to the 5th is the identity, B squared is the identity, and of course BA is now A to the 4th B. That's D5. Okay, now A to the 6th is just A to the 5th times A to the 5th is the identity. Okay, and then A to the 8th is just A cubed, and A to the 10th is just E. Okay, so we just have these 5 elements, that's in K. Okay, but since A squared is a commutator, automatically K is a subgroup of the commutator subgroup of D5. Okay, now if we now show that D5 mod K is abelian, that'll be enough. Okay, so okay, so we can actually look at just compare the order of K to D5. So first of all, K is normal in D5 since K has 5 elements and D5 has 10 elements. The index of K in D5 is 2. A subgroup of index 2 is a normal subgroup, so K is normal. Not only that, but since it's normal, we can take the quotient, and D5 mod K is a group of order 2. You have a group of order 2. Groups of order 2, are automatically abelian because there's only so automatically D5 mod K is abelian. So D5 prime is contained in K, and so D5 prime equals the subgroup generated by A squared, also known as the subgroup generated by A. And just think, if you want, you can think about why is it a group of order 2 abelian. It's just because there's only a few different ways to multiply things. It has 2 elements. The identity element, you multiply that by doing E times E. You have E times A, and just the group law says that has to be A. You have A times E. A group, the axioms of a group say that has to be A. Then A times A. If it can't be A because then A would be the identity, so it has to be E. Okay, and if I switch any of these two, I get the same thing, right? So E times A is A times E is A, and E times E is E times E, and A times A is A times A. Okay, so the order of multiplication doesn't matter. We have an abelian group. That's just maybe too much detail there. Okay, so anyway, we've shown that the commutator of D5 is the subgroup generated by A, this subgroup of index 2. And finally, we have the quaternions. You have to compute the commutator subgroup. Let's start by computing the commutator of I and J. That's just IJ, I inverse J inverse. Okay, I inverse is just okay, I mean there's so many different ways to do this, it just depends, but I'll try and list down the properties that I use. Okay, it really depends, but we're gonna say that we're gonna work with the fact that IJ is minus JI. Okay, and if we do that, IJ is minus Ji, I inverse J inverse. I times I inverse is just the identity, J times J inverse is just the identity, so you have minus 1. Okay, and we're using one possible description of the quaternions, that's as plus or minus 1, plus or minus I, plus or minus J, and then plus or minus K, where K is just IJ, and all these laws. Sorry again. Okay. Anyway, so the commutator of I and J is -1. So let's see if Q, take K to be the subgroup generated by -1, and see if Q mod K is abelian. If it is, then we can stop. So I mean, it turns out it is a good hope for it to be abelian, because when you mod out by k, it's like saying that the plus or minus doesn't matter, and if the plus or minus doesn't matter, this just says ij is ji, So anyways, so we let k just to be the subgroup plus or minus 1 in Q. And then let's look at Q mod k. Okay. Now, so the elements, we're going to denote the elements of Q mod k by bars. So we'll just put let 1 bar be 1 times k, I bar be the coset of I, j bar to be the coset of j, k bar to be the coset of little k. Okay. And now when I compute ij and ji, like ij is k and ji is negative k, but negative 1 is in the subgroup k, so negative k bar equals k bar, so ij is ji when I put bars over everything. Let me try and summarize. Okay, so over here we have an equation in Q. We have ij equals negative ji, and in Q mod k, we have I bar j bar is j bar I bar times minus 1, but the minus 1 is an element of k, so it's kind of absorbed. Okay. And so Q mod k is just the group, 1 bar, I bar, j bar, ij bar, right, which is an abelian group where ji is the same as ij, and I squared is 1, j squared is 1. In the Quaternions, I squared is negative 1, but when you mod out by k, you're saying like negative 1, the sign doesn't matter. So if the sign doesn't matter, I squared is like 1 or negative 1, that's the same thing mod k. Okay. So Q mod k is abelian. Okay. So that therefore k is contained in, or sorry, so therefore the commutator subgroup is contained in k, and then therefore the commutator subgroup equals plus or minus 1. Okay, so that's the end of question 1. Let's see, for question 4, we have to compute the center of this group of upper triangular matrices. I hope my hint was kind of helpful, but let me just, so I tried to work with in class. I tried to give you like some hints on how to work it out, but I'll just, in this solution, I'll just like start from the answer. So H is this subgroup of GL3. Oops, sorry. And let's let K, this is going to be 1, 0. I'll put a B. And B is any real number. Okay, we're going to prove that the center of H is K. Okay, first let's check that K commutes with anything in H. this commutes with anything in H. Oh, I need, maybe I'll make this a D. So, to compute that's this matrix and this matrix, and we have to do it the other way. Okay, we have computed, we have A, and we have D plus B, oops, this is C, and since D plus B equals B plus D, this is the same thing as we got before. Okay, so that proves that this matrix is in the center of H. It's not in the center of GL3, but it is in the center of H. Well, I mean, it is also in the center of GL3 if D equals 0, but otherwise no. Okay. So now let's try and figure out, let's try and prove if we have a matrix like this in the center, let's try and prove that A equals C equals 0. Okay, so now suppose this matrix, oops, is in the center of H. Well, then you should be able to multiply by, should commute with any matrix. I mean, you don't have, I'll just choose a simple one. So then when I compute this product and I compute it in the reverse order, it should be the same, right? So when I compute this product, I get 1, 0, 0, and then I get A plus 1, and then I get 1, 0, and then I get B, C, 1. And when I do it in the reverse order, what do I get? Well, I get 1, 0, 0, of course, and then I get A plus 1 here, then I get 1, 0, and then I get B plus C, and then I get C, and then I get 1. In other words, if this, for this matrix to be in the center of H, this matrix has to equal this matrix, which means B plus C equals B. So therefore B plus C equals B, which means C equals 0. Okay, and now we'll just switch the 1 to here and then do the same process. B plus C equals 0. We do right, what do you get? And if you do it the other way, you get A1, 0, and then you get B, C plus 1, and then 1. In other words, A plus B equals B. So that implies that A equals 0. And so we've shown in order for a matrix to be in the center, A and C have to be 0. In other words, our element is in our subgroup that we started with at the beginning. So therefore that shows us that the center of H consists exactly of these matrices. Okay. The last part of the argument says that any matrix that commutes with every matrix in H looks like this, and then before that we had shown that any matrix like this commutes with every element of H. Okay, so this is our center. Now let's move on to question 5. Okay, we have after a lot of thought, this is a group action. Okay, let's try and show it. Okay, so we have to let f is just going to be an arbitrary polynomial with integer coefficients. Sigma and tau are going to be permutations. Okay. And now, first let's do E, the identity, times F. Well, the definition of this group action says that we replace, like we substitute X, the identity of 1, X, the identity applied to 2, X, the identity applied to 3. The identity doesn't change 1, 2, or 3, so when you apply the identity permutation, you just get F back, and that's the first axiom of a group action. Okay, so that's one thing. Now the other thing to check, so we've shown that 1 times F equals F, and we also have to check that sigma tau F is just sigma tau F. Okay, so let's do that. Let G be tau F, and the definition of, I think in class I might have done like tau sigma, but it's fine. Okay, so what is the definition of tau F? Is that G of x1, x2, x3 is just fx tau 1, x tau 2, x tau 3. Okay. Now, if we just substitute, we're just going to substitute y's for x's so that we can compute a formula for sigma g. So we'll look at g, y1, y2, y3. Well, that's just f of y tau 1, y tau 2, y tau 3. Okay, how does that help us? Well, now we're going to apply sigma to g. Because what is sigma of g is just, sigma of g is just, of x1, x2, x3 is just g of x sigma 1, x sigma 2, x sigma 3. And now to find g of x sigma 1, x sigma 2, x sigma 3, we're going to call y1 x sigma 1. Okay, so we now substitute y1 equals x sigma 1, y2 equals x sigma 2, y3 equals x sigma 3. And when we do that, that tells us that g of x sigma 1, x sigma 2, x sigma 3, well, so that's just g of y1, y2, y3. Well, that's just f of y tau 1, y tau 2, y tau 3. And now what is y tau 1? Well, if tau 1 is 1, then y tau 1 is like we've made this substitution, yi equals x sigma I. So now when we see f of y tau 1, well, make this substitution, y tau 1 is just x sigma, and then the I is tau 1, so we put sigma tau 1. So this is just f x sigma tau 1, x sigma tau 2, x sigma tau 3. In other words, this is just sigma tau times f. Okay. And g of x sigma 1, x sigma 2, x sigma 3, that is just the definition of sigma g. And sigma g is just tau f, so that's just sigma of tau f. So we've shown that sigma of tau f is just sigma tau of f. So we have a group action. That's pretty much the end of it. I'm sorry if this one caused you as much confusion as it does me, or as it did me. Once you think about it a certain way, it is less confusing, but it is kind of hard to remember to get things straight. So again, I'm sorry about that. Okay, thank you for watching.